So we're going to be looking at the topic of statics and in particular systems on inclined planes. So here we have a diagram showing an inclined plane, and in problems involving inclined planes what we do is we simplify the modelling process by, instead of resolving horizontally and vertically, we resolve perpendicular and parallel to the plane. And what you find might help sometimes is if you actually kind of fill in not just horizontal but a vertical kind of, so you get this crosshair sort of diagram like this, so that you can fill in all the angles around. Now the reason we'd resolve perpendicular and parallel to the plane is, as you can see in this system, I've got two forces acting parallel to the plane and I've got one acting perpendicular. So out of the four forces, three of them are acting in this parallel and perpendicular to the plane direction. So it makes life a lot easier. It means the only force I have to resolve for is this weight force. Okay, I mean, you can resolve horizontally and vertically, it will work, but it means that you have to then use components of forces, so resolve using cos and sine for r, f and t, and that obviously makes things a little bit trickier and there's more room for error. Now, just a note on this, there are some further mathematical reasons as to why we would resolve parallel and perpendicular to the plane, and that will come up in our next topic, dynamics of moving particles. So let's look at our first example. The first example says a particle of mass 15 kilograms is resting on a rough plane inclined at 20 degrees to the horizontal. The particle is on the point of slipping down the plane, and we want to find the coefficient of friction between the particle and the plane. So just like any other problem, we're going to start off by drawing first of all a diagram. So this is going to be my inclined plane. It's a nice big drawing, so it's going to be nice and clear. Here's my particle resting on my inclined plane. Now we was told it was a mass of 15 kilograms, so I'm just going to draw the weight coming down. Remember that this is a weight, so it's 15g. The inclined plane I've been told is 20 degrees, so let's just put the 20 in on the incline there. Now it said the particle's on the point of slipping down the plane, so I mean we're going to be resolving parallel and perpendicular to plane, so I tend to draw this kind of crosshair regardless into my diagram. In some systems it helps to put the horizontal and verticals in, but at the very least I'm going to put a crosshair to represent the parallel and perpendicular to plane, and it helps with the resolving, and you'll see why in a moment. So what we have is that the particle's on the point of slipping. That means the particle would move down the slope, and so the friction, because it's a rough slope, would act up the plane. Next we have a normal reaction, because this weight is pushing down on the plane. Remember, a normal reaction happens perpendicular to the surface and the point of contact, so the reaction is going to act perpendicular to the plane. Now, diagram's almost complete. The only thing that's left to do is kind of complete these angles, because I'm going to have to resolve for this force here. So if I've got 20 degrees here, you can see I can make this kind of right angle shape, right angle triangle, sorry. So this angle here must be 70 degrees, and that must mean as I pair this angle here must be 90 degrees. Remember, the angles going round on a diagram usually fairly straightforward to do, because they're going to come in pairs that sum to 90 degrees because of the properties, because we're always working with right angle triangles, and then because we're always resolving within a right angle. Okay, so that's our diagram draw. Now what we've been asked to find is a coefficient of friction. Now I know for a coefficient of friction, if this is on the point of slipping, I know the fact that F equals mu r. And this is probably one of the first things we want to state, because I'm trying to find the coefficient of friction, because it's the only equation we know, or only fact we know about the coefficient of friction. So this means I'm going to need to find my friction, and I'm going to need to find my reaction. And once I've got both of those, finally I can find the coefficient of friction, mu. What's nice about this problem, like many of the problems involving systems of forces, is that if we didn't think about this and we just plodded on and resolved, so let's say resolve vertically first not vertically, of course, because we're going to be horizontal, perfectly to the plane. If we just carry on and resolve, then what we'll find is we'll find most of the work that we need to answer this question anyway. So this is to resolve perpendicular to the plane. So acting perpendicular to the plane is my normal reaction. There's no other force acting perpendicular to that plane. Remember, the friction that's acting parallel to the plane does not interfere with this reaction, because these two forces themselves are perpendicular. Okay, so then acting in the other direction, I have this 15g, so minus 15g, but it's not the whole 15g, it's just a component of the force, which when I resolve round, so we're resolving round this way, resolve through the angle I'm turning, so it's through cos of 20 degrees. And this is an equilibrium, so there's no movement, there's nothing happening here, so it's equal to 0. Now, what I can do is I can add 15g cos 20 to both sides, and I will then find my reaction. So my reaction is given as 147 cos 20. And I'm just going to leave it in terms of cos 20 because there's not massive amounts of working I have to do here. So I'm going to leave it as cos 20 because then I'm going to get a really accurate answer in a moment. Okay, so I've resolved perpendicular to the plane. What I could also do is resolve parallel to the plane, and by resolving parallel to the plane, I'm going to get an equation in F. So resolving parallel to the plane, remember it's not resolving equals, sorry, a bit of a slip there. So acting up the plane we have the friction, and then we look at the weight, and the weight has a component of force that acts down the plane. That's the force pulling the particle down the plane. So we get minus 15g cos 70. And again, this is an equilibrium, it's on the point of slipping, so nothing in the system is changing just yet. So I'm going to add the 15g cos 70 to both sides. And so I get F is equal to 147 cos 70. Now, as I said, like most questions, we start off just by resolving in the correct directions, parallel and perpendicular to the plane. And we form most of the information that I need. And even if you just do this, actually all the marks that are left are just a couple, because what we're going to do is just use this equation now to find mu. So using this equation to find mu, I'm going to substitute in F, so 147 cos 70. And I'm going to substitute in R, so I get 147 cos 20 times by mu. So if I divide by the 147 cos 20, what we're going to get left with is mu is equal to 147 cos 70 over 147 cos 20. And so mu, when I work this out, comes out as 0.36, correct to 2 decimal places. Now hopefully you can see that these problems really don't differ much from the problems that have been looked at so far already in statics. The only difference is, because I'm on an inclined plane, I'm resolving in a different direction, parallel and perpendicular to the plane. The whole skill of resolving, etc., that doesn't change in any way, shape or form. And you'll see as the problems get a little bit more complicated, especially when we're resolving parallel and perpendicular to the plane, this whole idea of using cos all the time and the angle you turn through will become a lot clearer as to why it makes the whole idea of modelling a lot simpler. Okay, well, let's look at example 2. Okay, so we've got a particle of mass m kilograms. It's resting on a rough plane inclined at 30 degrees to the horizontal. The coefficient of friction between the particle and the plane is 0.4. A force of 100 newtons acts on the particle up the line of greatest slope of the plane so that the particle is in limiting equilibrium. Find the mass of the particle. Okay then. Well, as always, we're going to start off. I need a diagram to represent this situation. So here is going to be my plane. Okay, so our planes always end up this kind of cheese wedge shape. I've got a particle of mass m kilograms. So there's my particle, and then acting downwards is m kilograms. So the weight is mg. As I said previously, I always draw a crosshair for inclined planes to represent that I'm going to resolve perpendicular and parallel to that plane. Now, we're told also that the plane is inclined at 30 degrees to the horizontal, so let's fill in some angles. And now, what I know is this is a right angled triangle here, so I don't bother drawing in the right angle, but we know that we can see that that's a right angled triangle, so that means all I have to do is to do this as a pair that add up to 90 degrees. And then I can also fill in this other angle here because this is a pair that adds up to 90 degrees. And now I've got all the angles I require in my diagram. I don't know what direction I need to resolve at the moment, but just fill in the angles, it takes 2 seconds. We're also told a force of 100 newtons acts on the particle up the line of greatest slope of the plane. So all this is saying really, it's just vocabulary to say that the force acts up the plane parallel to the plane. Okay, so there's that force of 100 newtons. It is a rough plane. We're told that the coefficient of friction between the plane and the object is 0.4. And so if it's on the point of slipping, that means that there is friction acting down the plane, because this force of 100 newtons will be pushing it to the point of slipping, so its motion or potential motion is up the plane. The final force, just to add on here, is that I need to put on the reaction. Okay, at this point we appear to have completed the diagram. Now, I want to find this mass here. I'm not really 100% sure how I'm going to go about finding this mass. So all I'm going to do really is I'm going to resolve parallel and perpendicular plane to start with and see where that takes me. And this is the approach to most problems like this. You may not see the answer laid out there before you, in front of you. It may not appear obvious, but what you're going to get marks for, organising your information. You're going to get marks for resolving and forming equations, because those equations ultimately are going to lead you to M in some way or another. Whether you get to M is another story, but at least you can take some of the sort of steps towards it. Once you take some of the steps towards it, you get a little bit closer, and you then may be able to see the solution to get in that mass. So, resolving perpendicular to the plane, both the friction and the 100 newtons force are perpendicular to the reaction, so I can ignore them. So I just get R minus mg cos of the angle I'm turning through, which is 30 degrees. And that is equal to 0. So adding mg cos 30 to both sides, what I get is that r equals, well, cos 30 is root 3 over 2, so I can call this root 3 over 2 mg. And actually what I could do is I could tidy up this with this g, and I could write this instead as r equals half of 9.8 is 4.9, so we could write this as 4.9 root 3 m. Now, in terms of value for the reaction, it's not too bad. Okay, it's not a numerical amount. I've still got m in there, but we can work with that. Okay, so that kind of leads us to a dead end. I can't solve this because I don't know what r is, so let's resolve parallel to the plane and see where that takes us. So I'm going to resolve in the direction of possible motion. It's a force of habit, okay, and it will make a little bit more sense when we come to dynamics. So acting up the plane, we have 100 newtons. Acting down the plane, I have F. And also acting down the plane, I have the component of the weight force when we resolve through this angle of 60 degrees. So I get minus mg cos 60 equal to 0. And so if I tidy this up a little bit, what we get is that we get 100 minus f. Cos 60 times 9.8 will give you minus 4.9 m equal to 0. Now, the problem I've got with these two equations is that I've got an equation in R and I've got an equation in F. So it's at this point I want to use friction, because friction can link the reaction to the friction. So if I say F equals mu R, what I can say then in that case is that F is equal to 0.4 times 4.9 root 3 m. And when I tidy this up, I get that the friction is in fact 1.96 root 3 m. What this means is, if I number my equations, 1, 2, I can sub the expression for F that I've just obtained from the friction, I can sub that into the equation I've got when I resolve parallel to the plane. So now instead what I have is 100 minus 1.96 root 3 m minus 4.9 m equals 0. And what's really important here is that you remember that we've got this equation F equals mu R. Let's highlight this a little bit. Okay, we've got this equation to link F and R. So that means when I've got a system equation, because I resolve in one direction and I get reaction, and when I resolve in another direction I get friction, when I want to reduce one of the variables, I always use this equation because I've got a link between F and R. Okay, and this is where some people sometimes get stuck. So that's why I say always resolve, because at least at this point with these two equations, you're part of the way there, you get some of the marks. If you don't remember to use that friction, you've got a couple of marks. Okay, but you'll get in the habit and you'll form a structure and then approach these questions in the long run. So let's solve this now anyway. I'm going to add 4.9m to both sides, and I'm going to add 1.96 root 3m to both sides. So we get that 4.9m minus 1.96 root 3m equals 100. Now you could, if you wanted to, at this point you could find a numerical amount for 4.9 take away 1.96 root 3. This is just the same as having 5m take away 2m. It's just that I've got expressions using surds. Another way of doing this is I could factorise the m out and say, okay, m times 4.9 minus 1.96 root 3 equals 100. And the reason I'm doing this is I'm just trying to find the most exact answer as possible. What happens in some questions, especially exam questions, is that you sometimes have to find exact answers, which means that you need to be able to do the algebra. You need to be able to manipulate to this level. They are the more challenging exam questions, but nonetheless, something that you may need to do. So the last step is then, if I got m factorised, so it's on its own, here we have a product. Essentially this would be the coefficient, and you could find this value and write it as a decimal if you're not really confident working like this. But this is going to give me the most exact answer, and when I finally finish by dividing 100 by 4.9 minus 1.96 root 3, you should get an answer of 12.06 kilograms to 2 decimal places. Okay, well I hope that made sense. This is a prime example of a mechanics question for me, because did I know how I was going to find the mass at the beginning? No. All I knew was I had to have the confidence that I have the skills and the approach to solve and find that mass. And so the initial thing, having drawn a diagram and organised my information, is that I know that I'm going to have to resolve. So I resolve in two directions that form two equations. Still didn't really know where I was going at that point. So what I did was looked at the equations, couldn't solve them simultaneously because I identified the fact that we had r in one of the equations and f in the other equation. So I had two separate variables. But that's when I identified friction equals mu r, as a useful tool to eliminate one of those extra variables. Okay. Once I did that, we ended up with a fairly straightforward equation in M to solve. And as I said at the end, if you can practice, if you can get to grips with trying to solve problems using these exact methods, it will improve your algebra skills, it'll improve your core maths modules, but most importantly, it means you can deal with the most challenging exam questions that can come up sometimes. If you struggle with that, then focus on just working with the decimals. Evaluate 1.96 root 3. Actually do the subtraction of the amount of M and simplify the process for yourself. If you get to the answer, you get to the answer, and that's fantastic. Okay, well, I hope that all made sense. Time to try an exercise.